Hello everyone, welcome to part 2 of Unit 3 Cloud Storage Systems. In this section, we will be seeing about online transaction processing, NoSQL database and popular cloud databases. Now let us start with online transaction processing. It is commonly called as OLTP systems. OLTP systems are designed to manage transaction-oriented applications where data is continuously entered, updated and retrieved in real time. These systems handle a very large number of simple and short transactions such as inserting records, updating account balances, processing payments, booking tickets, or generating bills. OLTP systems are widely used in industries like banking, retail, e-commerce, airline reservation systems, and online shopping platforms where fast response and accurate data handling are extremely important. One major requirement of OLTP systems is real-time processing. Users expect immediate responses whenever they perform a transaction. For example, when a customer withdraws money from an ATM or places an online order, the system must process the transaction instantly. Another important characteristic is short response time. Even when thousands of users access the system simultaneously, the database should remain responsive and efficient. Traditionally, OLTP systems often dependent on vertical scaling where system performance is improved by increasing the power of a single machine such as adding more CPU or memory. However, modern cloud systems also use horizontal scaling where additional machines are added to distribute workloads across multiple servers without sharing primary resources. Overall, OLTP systems focus on fast, reliable, and consistent transaction processing for real-time applications. Let us now understand the core features of OLTP systems. One of the most important features is high concurrency. OLTP systems are designed to support a large number of users and transactions at the same time without slowing down the system. For example, thousands of customers may access an online banking system simultaneously. Another major feature is ACID compliance. OLTP systems follow the ACID properties, which denotes atomicity, consistency, isolation, and durability. These properties ensure that transactions are processed reliably and that the database always remains in a correct and consistent state. OLTP systems also support real-time processing. Transactions are processed immediately so users can access updated information without delay. Data integrity is another critical requirement. The system uses mechanisms such as constraints, validation rules, and triggers to maintain accurate and consistent data while preventing corruption. These systems are mainly optimized for simple and short transactions rather than long analytical operations. Their goal is fast execution and quick response time. Finally, OLTP systems include strong backup and recovery mechanisms. If there is a system crash, hardware failure, or power interruption, the data can be recovered quickly without losing important transactions. Together, these features make OLTP systems highly reliable for real-time business applications. Next, benefits of OLTP systems. One major benefit is improved efficiency. Since OLTP systems can process huge volumes of transactions quickly and accurately, organizations can perform operations smoothly and reduce processing delays. Another advantage is increased data accuracy. Because OLTP systems follow ACID properties, the database remains consistent even during hardware failures, power outages, or unexpected interruptions. These systems also support real-time decision making. Since updated information is always available instantly, businesses can make quick and informed decisions based on current data. OLTP systems also help improve customer experience. Fast transaction processing reduces waiting time and increases user satisfaction. For example, customers expect immediate confirmation during online banking or shopping transactions. Another important benefit is scalability. OLTP systems are designed to handle growing transaction volumes efficiently as businesses expand. Overall, OLTP systems provide speed, reliability, accuracy, and scalability, making them essential for modern real-time applications. Now let us look at some widely used OLTP database systems. One of the most popular systems is Oracle Database. It is widely used in enterprise applications because of its reliability, security, and high transaction processing capability. Another commonly used system is Microsoft SQL Server developed by Microsoft. It is popular in business and enterprise environments for managing transactional databases. MySQL is also widely used, especially in web applications and online services because it is open source, lightweight, and easy to manage. Next is PostgreSQL, known for its strong standards, compliance, advanced features, and reliability in handling complex transactional operations. Another enterprise level OLTP system is IBM DB2 developed by IBM, commonly used in banking and large scale enterprise applications. Finally, Amazon Aurora is a cloud native relational database service provided by Amazon. It offers high performance, scalability, and availability for cloud applications. These OLTP systems are widely used because they provide fast transaction handling, data consistency, and reliable database management for real-time applications. Now let us move to NoSQL database. NoSQL databases are also called non-relational databases or not only SQL databases. Unlike traditional SQL databases, NoSQL databases do not require a fixed table schema. This means they can store different types of data more flexibly, including structured, semi-structured, and unstructured data. For example, modern applications generate data in many forms such as JSON documents, images, videos, social media content, sensor data, and logs. Managing all this data using traditional relational tables becomes difficult, so NoSQL databases provide a more flexible solution. NoSQL databases support different storage models based on application requirements. The first type is the key value store. In this model, the data is stored as a pair of keys and corresponding values similar to a dictionary. Examples include Oracle NoSQL database, Redis, and Amazon DynamoDB. The second type is the document-based store. Here, the data is stored in the form of documents, usually JSON-like structures. Examples are MongoDB and Couchbase. The third type is column-based store, where the data is organized into columns instead of rows. Examples include Google Bigtable, Apache Cassandra, and Apache HBase. Finally, graph databases are designed to store relationships between connected data. An example is Neo4j. Overall, NoSQL databases provide scalability, flexibility, and efficient handling of large modern datasets. Let us understand why NoSQL databases became popular and how they differ from traditional SQL databases. Large internet companies such as Amazon, Google, LinkedIn, and Facebook started using NoSQL databases because traditional relational databases were not always suitable for handling massive amounts of rapidly growing unstructured data. As data processing requirements increased exponentially, organizations needed databases that cloud scale easily and handle dynamic data efficiently. NoSQL databases provided a more cloud-friendly and flexible approach for such applications. Traditional SQL databases are relational databases. They use structured tables with predefined schemas and structured query language for managing data. In contrast, NoSQL databases are non-relational and support dynamic schemas. This means the structure of stored data can change easily without redesigning the entire database. SQL databases are very effective for applications requiring complex queries and strong consistency, especially multi-row transactions. NoSQL databases are more suitable for handling unstructured or semi-structured data such as documents, JSON files, social media content, and real-time big data applications. Another important difference is scalability. Most SQL databases mainly depend on vertical scaling, where the performance of a single server is increased. NoSQL databases support horizontal scaling, where more servers can be added easily to distribute data and workload across multiple machines. In many large-scale applications, NoSQL queries can also provide faster performance because the data models are optimized for distributed processing. So overall, SQL and NoSQL databases are designed for different application requirements, and modern cloud systems often use both depending on the use case. Let us now discuss the major advantages provided by NoSQL Cloud Database Services. The first advantage is that NoSQL databases are developer-centric. They are designed with flexibility in mind and support multiple types of data models such as document-based JSON data, fixed schema data, and key value storage. This allows developers to choose the most suitable model based on application requirements. Another important advantage is openness and portability. NoSQL services can work with both document-oriented and fixed schema models. Applications developed using NoSQL databases can run either in cloud environments or on-premises systems without major modifications. This reduces platform lock-in and provides deployment flexibility. Ease and simplicity are also major benefits. Most NoSQL cloud services provide software development kits or SDKs and support multiple programming languages such as Python, Go, Node.js, and Java. Because of this, developers can build and deploy applications quickly using user-friendly graphical interfaces and APIs. Elastic scalability is one of the strongest advantages of NoSQL systems. As application traffic and data volume increase, the database can automatically scale by adding more resources. This helps maintain low response time and stable performance even during heavy workloads. Another key benefit is high availability and fault tolerance. Many NoSQL databases provide automatic failure detection and failover mechanisms. If one system fails, another server immediately takes over, ensuring that applications continue functioning without major downtime or data loss. Some cloud NoSQL services even provide availability levels of up to 99.95%, which is extremely important for business critical applications. Overall, NoSQL databases provide flexibility, scalability, simplicity, and a high availability, making them highly suitable for modern cloud and big data applications. Now, let us look at some popular cloud databases widely used in distributed and big data environments. Some of the popular cloud databases used in modern distributed systems are Apache HBase, MongoDB, and Apache Cassandra. These databases are widely used for handling large-scale cloud data because they provide scalability, high performance, and fault tolerance. Let us now understand the architecture of Apache HBase. HBase is a distributed column-oriented NoSQL database built on top of the Hadoop Distributed File System or HDFS. It is designed to store and manage very large datasets across multiple machines. We can compare this architecture to a large multi-specialty hospital. In the architecture, the H master acts as the master node responsible for managing the entire HBase cluster. It handles region allocation, load balancing, and metadata management. This is similar to a hospital administrator who manages all departments and coordinates the entire hospital operations. The actual data is managed by region servers. These servers store different regions of HBase tables and handle client read and write requests. Region servers can be compared to different hospital departments such as cardiology or neurology where the actual patient treatment and activities happen. Zookeeper is another important component used for coordination and fault tolerance. It monitors server status and helps in failover management if any node fails. This works like a hospital control room that continuously monitors all departments and manages emergencies if any department faces issues. At the storage level, HDFS is used to store data in a distributed and reliable manner. This can be compared to the hospital's central medical record storage system where all patient records are securely maintained and backed up. Finally, clients communicate with HBase through APIs to perform data operations efficiently across a distributed environment. These clients are similar to doctors or patients requesting access to medical records and services. So overall, just like a hospital distributes responsibilities across departments while maintaining coordination and reliability, HBase distributes huge amounts of data across multiple servers efficiently. Let us now look at the major components of Apache HBase in a little more detail. The first component is the HMaster. The HMaster acts as the master node that manages the entire HBase cluster. It is responsible for assigning regions to region servers, balancing workload across servers, and handling schema or metadata management. In simple terms, it controls and coordinates the overall system operations. The next component is region servers. Region servers handle actual client read and write requests. Each region server manages multiple regions where each region stores a portion of the HBase table data. These regions are physically stored in HDFS. Another important component is Zookeeper. Zookeeper provides coordination and fault tolerance within the cluster. It keeps track of active servers and helps them failover management if any server becomes unavailable. This ensures high reliability and continuous operation. Apart from these, there are a few additional supporting components. The client communicates with the HMaster and region servers to perform data operations such as reading and writing. Finally, HDFS acts as the distributed storage layer where all the actual data is stored securely across multiple machines. Together, these components help HBase provide scalable, reliable, and high-performance distributed database management. Understand how data flows inside Apache HBase and the advantages of this architecture. The process begins with the client. The client communicates with the HMaster and region servers to perform read and write operations. The HMaster manages the cluster and assigns different data regions to the appropriate region servers for balanced workload distribution. The region servers then handle the actual storage and retrieval of data. The data is finally stored in HDFS, which provides reliable distributed storage. Meanwhile, Zookeeper continuously monitors the system and ensures proper coordination and server availability. If any server fails, the Zookeeper helps manage failover mechanisms to maintain uninterrupted operation. This architecture provides several important benefits. The first benefit is scalability. HBase can handle extremely large datasets by simply adding more servers to the cluster. The second benefit is fault tolerance. Since data is distributed and replicated using HDFS and monitored through Zookeeper, the system continues functioning even if some nodes fail. Another major advantage is high performance. HBase is optimized for fast read and write operations, making it suitable for real-time big data applications. Overall, HBase provides scalable, reliable, and efficient distributed data management for cloud environments. Next, MongoDB architecture. Let us understand this architecture using a simple analogy based on food delivery service. Imagine a large food delivery company operating across many cities. The application represents the food delivery app used by customers to place orders. The MongoDB driver acts like the order communication system that transfers customer requests to the backend service. The query router or Mongoose acts like a central call center. It receives customer orders and forwards them to the correct restaurant branch based on location and availability. MongoDB uses sharding to distribute data across multiple servers. These shards can be compared to different restaurant branches located in different areas. Each branch manages a portion of customer orders and delivers data. Inside every shard, there are replica sets with primary and secondary nodes. The primary node acts like the main kitchen where the actual food preparation and order processing happen. The secondary nodes act like backup kitchens that continuously maintain copies of order information. If the main kitchen becomes unavailable, so a backup kitchen immediately takes over, so customer service continues without interruption. This distributed architecture helps MongoDB achieve high scalability, fault tolerance, and efficient handling of large amounts of cloud data. Let us now understand the major components of MongoDB architecture. The first component is the application and driver. The application interacts with MongoDB through a driver which acts as a connector between the application and the database. The driver sends queries to the database and receives responses back from the system. Next comes the query router, also called Mongoose. The query router receives client requests and routes them to the correct shard in the MongoDB cluster. This helps distribute queries efficiently across multiple servers. Another important concept is sharding. MongoDB uses sharding to divide data across multiple servers for better scalability and performance. Each shard stores only a portion of the overall dataset. The shard key determines how the data is distributed among the shards. MongoDB also supports replication for fault tolerance and high availability. Each shard contains replica sets consisting of primary and secondary nodes. The primary node handles actual read and write operations, whereas the secondary nodes continuously replicate data from the primary node and act as backups. If the primary node fails, one of the secondary nodes automatically becomes the new primary node, ensuring uninterrupted operation. Together, these components allow MongoDB to provide scalable, distributed, and highly available cloud database services. Let us now understand the architecture of Cassandra using a railway network analogy. Imagine a large railway reservation system operating across multiple cities. In Cassandra, the entire system is organized as a ring cluster. This can be compared to a circular railway network where many railway stations are connected together. Each node in Cassandra acts like an individual railway station. Each station can independently handle passenger bookings and ticket enquiries. Similarly, in Cassandra, every node can independently handle read and write operations. Unlike systems with a central controller, Cassandra follows a peer-to-peer architecture. This means all nodes are equal, just like railway stations directly communicating with each other without depending on one central station. Cassandra also uses something called the gossip protocol. This is similar to railway stations continuously exchanging status updates with nearby stations regarding train schedules, delays, or operational conditions. In Cassandra, nodes exchange health and status information to keep the cluster updated. Another important concept is replication. Data is copied across multiple nodes, similar to maintaining backup reservation records in multiple railway stations. So, even if one station becomes unavailable, the reservation information can still be accessed from another station. During a write request, data is stored in multiple nodes based on the replication factor. During a read request, Cassandra retrieves data from the fastest available node. This decentralized architecture makes Cassandra highly scalable, fault tolerant, and suitable for large cloud based applications. Let us now understand the major components of Cassandra architecture. The first component is the ring cluster or data center. Cassandra organizes nodes in a ring-based structure where multiple servers are connected together as a part of distributed cluster. Since there is no central master node, the system avoids a single point of failure and becomes highly fault tolerant. Next are the nodes. Each node is an independent database server capable of handling both read and write operations. All nodes are equal in Cassandra, meaning there is no master-slave relationship. Cassandra follows a peer-to-peer distributed architecture. Every node directly communicates with the other nodes in the cluster. To maintain coordination, Cassandra uses the gossip protocol. In this protocol, nodes periodically exchange status information with a few random nodes. This helps the cluster continuously stay updated about node health and system changes. Another important concept is the replication factor. Data in Cassandra is replicated across multiple nodes to ensure high availability and reliability. The replication factor determines how many copies of the same data are maintained in the cluster. Finally, we have the read and write path. During a write operation, data is stored across multiple nodes according to the replication factor. During a read operation, Cassandra retrieves data from the fastest available node to provide efficient performance. Together, these components make Cassandra highly scalable, decentralized, and fault-tolerant for cloud-based distributed storage systems. Let us now understand how Apache Cassandra works and the benefits provided by its architecture. In Cassandra, the data is distributed across multiple nodes using a technique called consistent hashing. This mechanism determines which node is responsible for storing a particular portion of the data. Each node stores only part of the total data set and handles a subset of read and write requests. This distribution improves scalability and reduces the load on individual servers. The gossip protocol continuously exchanges status information among nodes so that every node remains updated about the health and availability of the cluster. Cassandra also uses replication to maintain multiple copies of data across different nodes. Because of this redundancy, even if some nodes fail, the data remains accessible from other nodes. If one node goes down, another node containing the replicated data automatically continues handling requests. This provides strong fault tolerance and high availability. Next, coming to the advantages, one major advantage of Cassandra is scalability. Large amounts of data can be handled simply by adding more nodes to the cluster. Another advantage is decentralization. Since there is no master node, the system avoids a single point of failure. Cassandra also provides high performance with fast read and write operations, making it suitable for large-scale cloud applications and real-time distributed systems. Difference between the architecture designs. Finally, this comparison helps us understand how the architectures of HBase, MongoDB, and Cassandra differ from one another. HBase follows a master-slave architecture where the HMaster manages the cluster and region server stores the data. It is tightly integrated with Hadoop and HDFS, making it suitable for big data processing environments. MongoDB uses a sharded architecture with replica sets. Data is divided into shards for scalability, while primary and secondary nodes provide replication and fault tolerance. It is highly flexible because it stores data in document format. Cassandra follows a fully decentralized peer-to-peer architecture. All nodes are equal and there is no central master node. This provides very high fault tolerance and scalability for distributed cloud applications. In terms of storage model, HBase is column-oriented, MongoDB is document-oriented, and Cassandra is also designed for distributed column family storage. So overall, each architecture is designed for different application requirements depending on scalability, fault tolerance, flexibility, and performance needs. We come to the end of this session. Thus, in this unit, we discussed various cloud storage systems and distributed database technologies used for managing massive amounts of cloud data. We understood file systems, distributed storage architectures like Google File System and Apache Hadoop, online transaction processing systems, and modern NoSQL databases such as HBase, MongoDB, and Cassandra. These technologies play a major role in providing scalable, reliable, and efficient cloud data management in modern cloud computing environments. Thank you.